My biggest criticism of this book is that it covers a lot of material in one or two sections. So, really, if I were to write this textbook, I would break up 11.4 into 3 or 4 sections at least. So, first, we're going to go through concentrations. Molarity should be a review, and that's what we're covering in this section, and then we'll cover some more. After that, we'll get to colligative properties and talk about several different kinds of colligative properties before we talk about how these things are affected by what's known as the Van Hoff factor. So just kind of keep in mind there's a lot of stuff going on inside of this section. Each one of these is essentially its own page in the online version of this textbook. We are going to spend most of this semester talking about the effects of chemical concentration. For example, two solutions contain the same chemical compound or compounds, but they react differently because the amount of solute per solvent is different. For example, we will see this semester that concentration dramatically affects the magnitude of the reaction, how far it goes, the speed of the reaction, the reactivity of the reaction, and with all those things comes a bunch of other issues we're worried about: toxicity, corrosiveness, carcinogenic properties, etc. So we will talk about the general chemical applications, then we can relate it to those other things. But first, we have to talk about how we measure chemical concentration. This chapter has 3 major ways of measuring concentration. Molarity, of course, is the chemistry standard. That's what we're going to use most often moving forward. This chapter focuses a lot on molality, which is primarily used for colligative properties, which we'll talk about in a bit, but this looks at the moles per kilogram. So really, how many particles are there per weight of solvent? So it's a little different unit, and it's not quite as easy for chemists to use in general. Next is mole fraction. This is also used for some colligative properties, but outside of that, it's mostly used to see when there are interactions between solvent and the solute that you want to look at closer. So how many particles of solute are there per particles of solvent, and how does that influence the properties of the solution? So molarity here should be a quick review. It's just the moles of solute per liter of solution. In this problem, we have 12 grams of magnesium chloride in a 130 milliliter solution. Well, since we need to have moles and liters, the easiest thing to do is just to change 130 milliliters to 0.130 liters. Just move the decimal over 3 spaces. To find the moles, we have to find the formula weight of magnesium chloride because this is an ionic compound or a salt. We know that magnesium, according to the periodic table, is 24.3 grams per mole, and each chlorine is 35.5 grams per mole, and there's 2 of them for a total formula weight of 95.3 grams per mole magnesium chloride. Now, at this point, we can set up the conversion factor. 12 grams of magnesium chloride divided by 95.3 grams per mole gives us 0.126 moles of magnesium chloride, 3 sig figs. So now we can just put the moles of magnesium chloride over the liters of solution. That gives us 0.969 molar magnesium chloride. Now, we have not labeled the solution. We have just assumed that this is water, and as long as it's just water, we don't have to label anything else. However, as we'll see later in this chapter, if we're using a different solvent, if we're using ethanol or acetone or methanol, all those things should be labeled in the concentration because that chemical also has other chemical effects. Again, as long as it's in water, we don't have to label that. So go ahead and try this problem really quick. What is the molarity of an 85 milliliter solution that contains 3.42 grams of KBr? Pause and start the video when you're ready to see the answer. So the formula weight for KBr is relatively simple. It's 39.1 grams per mole plus 79.9 grams for the bromine gives us 119 grams per mole. We have 3.42 grams and 119 grams per mole gives us 0.0287 moles of KBr, again 3 sig figs. we had 85 milliliters of solution. So if we move the decimal spot over 3 spaces, that's 0.0850 liters. So we put the moles of KBr over the liters, gives us a 0.338 molar KBr solution. This semester, we are actually not going to make that many solutions, but what we are going to have to do a lot is figure out exactly how much chemical is in the solution we are using. So, one of the ways that we teach this now is that molarity is a conversion factor. And this makes life a lot easier because we can figure out where we're starting and where we're finishing. You can also use the molarity equation if you want. That involves cross multiplication, but that's fine. So, for example, if I say I have 30 milliliters of a 0.5 molar NA solution, I can plug in my milliliters to liters, I can plug in my 0.5 to molarity. The other thing I can do is say, oh, a 0.5 molar solution is 0.5 moles of NaCl per liter. This lets us use the conversion factor approach. Because I have milliliters to liters, I have to divide by liters and multiply by moles. I can do this calculation very quickly. Not that the molarity equation is hard, but if you're doing a lot of these calculations, this goes very, very fast. Now that I have the moles, I can multiply it by the grams per mole according to the periodic table to get the moles of NaCl I need. All right, so this is a much simpler problem. Figure out how many moles of NaOH are going to be in 44 milliliters of a 3 molar NaOH solution. So you can either use the molarity equation or you can use the conversion factor. Okay, so I use the conversion factor. Again, I think it's worth keeping in mind that it's easy to find this way. We know that 3 molar NaOH is 3 moles of NaOH per liter. We have 44 milliliters, so I've got to convert that over to liters, 0.0440 liters. Divided by liters times moles gives us 0.132 moles of NaOH. If I wanted to, I could calculate to find the grams from here, but that's fine for now. So this is a similar type of problem. In this case, we need to get exactly 0.25 moles of HCl into a reaction. We're asking how many milliliters of a 6 molar HCl solution should be used. Now this can be solved either by the mathematical molarity equation seen on your screen, molarity equals moles over liters, or it can be solved by the conversion factor approach. But I will note that the conversion factor approach is going to be much faster here. But I will show you both answers in the next 2 slides. So either way you solve it, you should be able to see comparatively how I did the same thing. So pause the video until you're ready to move forward. So in the conversion factor approach, I know that there are 6 moles of HCl per liter. Now I'm starting with units of moles of HCl, so that is my starting point. I'm going to divide by moles and multiply by liters. And so I've got an answer in 0.0417 liters, or that's just 41.7 milliliters of this solution. That's it. That's the whole problem. For the equation approach, this takes a bit more work because our liter is in the denominators. So in order to solve any algebraic problem, we have to get liters off the denominator, or else we are always going to get the wrong answer. We can actually see that in the units as we solve. So I'm going to cross multiply both sides by liters, and when I do that, that crosses off the right-hand side, and that leaves me on the left side with liters solution times 6 molar equals 0.250 moles. At this point, I'm going to cross divide both sides by 6, and that's going to give me liters of solution equals 0.250 moles divided by 6 moles per liter. Now, I changed the molarity to moles per liter because now we can see that moles and moles are going to cross out. That will be left with units of 1 over liters, which is equivalent to liters. And now that gives me an answer of 0.0417 liters, and I'm just going to convert that to 41.7 milliliters. So same answer, different approach.